Good morning, everyone. A very warm welcome to the fifth session of Semiconductor Nation Campus Connect webinar series, which is an initiative under Semicon India Future Skills by ISA. So in this webinar, we are intended to cover the entire journey from SAN to electronic systems. The slide shown here gives us the global picture of how this journey starts, what are the things that are covered into this journey. So in this series, we are intended to cover one block at a time, as you can see from this slide deck. And we are intended to give faculties and the students an overview of how it starts from a sand and how a mobile phone is in our hand. So the previous sessions of this series are also available on ISA's YouTube channel. And today's session will also be recorded and it will be made available to the viewers anytime they are intended to watch it. And also we are like these sessions can be used by the faculties as a part of their lecture as and when suitable during the course content. And also we request you to post your questions and suggestions in the chat box, which we will take towards the end of this session. So the previous two sessions we talked about IP design. This session we'll be covering SoC design verification. And this topic will be covered in two sessions. So for today's session, the what and why part of it will be talked about. And in the next session or in the next month's session, we'll see the how part of it. So now let's introduce our speakers. So it gives me an immense pleasure to introduce to you all to our today's speaker, Mr. Ravinder Pal Singh, who is a semiconductor industry professional with more than 25 years of experience in VLSI design industry. He is currently serving in ST Microelectronics as a senior group manager. He is a graduate from NIT Kurukshetra and holds expertise in SoC design. Most of his experience has been in functional verification, both at IP and SoC levels. A very warm welcome to you, Mr. Singh. Over to you.
Thank you, Sushma. So firstly, a very warm welcome to everyone on a very cold morning like this. So let me share my presentation. Okay. SoC verification is an important step, an important part of the SoC design flow. And today's talk, the aim of today's talk is to give a very high-level overview of this area and what all concepts are involved in this function. So just first off, while I present, actually I cannot get to see the participants, so I cannot see how people are reacting. I cannot know the reaction. So feel free to put into the chat and let me know, through Sushma that if I need to slow down or speed up. Okay, so as Sushma said, we will go through the introduction and we will cover this topic in two parts, now and one next month. So the why and the what and the how, this we will cover overall for this topic. The why and the what part will be covered in this part, and then we will cover the how part in the next one. Okay, so electronics applications are an integral part of our daily lives. We all, can we imagine ourselves without a mobile phone today? Or we have, TVs. Everyone has TV at home for entertainment. The cars of today, average car that is on the road today that we see has high electronic content, of the order of 50 to 60 SoCs in an average car. And that goes on increasing for high-end cars. And we know that for cars of the future, like autonomous driving cars, they will be completely controlled by electronics, software and hardware. So high electronic content there. And also now in the medical electronics, a lot of things are being done with the help of electronics. We know that we have robotic surgeries being performed. So all this is enabled by electronics. And also the list of these devices goes on increasing day by day as we make more and more technological advancement. We have more and more applications in entertainment, in convenience sectors. There is one common basic expectation from all of us as consumers of these electronic devices, as users of these electronic devices, that we expect all of them to work flawlessly without any issues. So when we see all these electronics, right, what is at the heart? What makes these things tick? So the heart is basically one or more SoCs. So all these embedded electronic systems are built around one or more SoCs. And again, there are two parts to it, the hardware part and also the software part, which have to work together correctly in concert together. So to make these electronics deliver the functionality that they're supposed to do in a flawless way. When we look at SoC, now what are we really talking about? What exactly is an SoC? So if you see at a very basic level, and by the way, this is a very oversimplified description of SoC, but basically it is a collection integration of different IPs. Okay, and IP is like different building blocks. So it could be digital building blocks, like you could have a processor core, you could have different IPs which give different functionality like UART functionality, I2C functionality. Let me just bring, okay, you could have specific IPs for doing a very specific function like video accelerators, or camera interface, display interface, etc. So all these are digital, the ones that you see in yellow. And there are also analog IPs in the chip. Clock generator. Every IC needs a internal clock generator. So there would be a PLL, which is analog. You could have A to D and D to A converter IPs. And there are invariably also on-chip RAM, ROM, which have components of both analog and digital. So this diagram is a very, as I said, very simplified diagram, but it could range from even a simpler IC with just a few IPs to very complex IC depending upon the target application. It could have multiple processor cores, order of 16, 32, even 32 cores, or it could have IPs which go into orders of 80 to 90 IPs for a complex network processor, for example. Or on the lower side, if you have IoT node SoC, that would have just a few blocks, maybe less than 10. So it ranges from a very simple, less number of IPs to very complex, high number of IPs, and everything in between. And basically, it has these kind of components. Okay, so this slide is basically an imagination exercise. So just imagine a typical everyday application. Most of us have microwave at our homes, and just imagine that you had a frozen pizza which you want to reheat. reheat in order to eat. And we know that nowadays microwave has a preset buttons for these things. So there is a button for frozen pizza. You just press that and microwave is supposed to heat the pizza in a few minutes. But what happens is after a few minutes, you hear the microwave bell ring and you see your pizza is actually burnt. It's supposed to heat it, but it's actually burnt. So what is happening here? So this could be happening due to a bug, either in the program, either in software programming of this function, or also it could be in the hardware. Again, these are hypothetical examples just to illustrate a point. So it could be due to either hardware or software bug. Now, consider a critical application. Let's discuss a futuristic application, which could be an autonomous vehicles. We know that in a few years from now, we will have vehicles which would be completely autonomous, which means, as the picture shows, that the passenger is actually reading the book and the vehicle is driving itself. So the vehicle is completely controlled by electronics. Millions of lines of code, hundreds of ICs controlling the entire operation of autonomous vehicles. Again, imagine, in such a complex system, let's say there is a small bug which causes a steering to suddenly turn when you are actually going at a high speed on the highway. Imagine what could happen, right? Nobody wants to be in that situation. So what are bugs after all? If you just Google the definition of bug, it is a bug refers to an error, flaw, a fault or flaw in a computer program or a hardware system, that is software or hardware. A bug produces unexpected results. Now, what could be typical causes of the bug? It could be incorrect. The source could be different things. It could be incorrect architecture, maybe the way a particular product has been architected. There's a problem there. That could be the source of a bug, and it doesn't handle certain situations well, that particular architecture. So that could be a source. Architecture could be right, but the implementation of that architecture into the actual product, that could have a problem. And this is, I think, the most common reason for the bug to be there. There could be omission of functionality. So functionality is specified, but for some reason that functionality has not been implemented into the end product. And that could cause a problem with the functionality. There could be performance related bugs. Imagine you're using a mobile phone and a high definition video, you're streaming a high definition video, and suddenly you start getting flickers. Normal definition works fine, but high definition video starts to create problems. That is because it's not able to be handled by the product. It's a performance issue of the product. And it could be either software or hardware. And the impacts we saw, it could be annoying impact like a burnt pizza, a phone hanging, things like that, or it could be dangerous or even fatal, as we saw the case of an autonomous vehicle, or even a surgical equipment. A problem in a surgical equipment could cause serious injuries, or even it could be fatal. And almost always it will cause a reputation or financial loss for the product companies, because if their products are there and they're buggy. Bad user experiences affects customer loyalty for brands. If you find a problem with a particular product of particular brand, you would not recommend that brand, right? Or think of even buying that brand in the future. So it affects the customer loyalty for brands. So how can we eliminate these bugs? It is only through thorough software testing and uh, the correspondingly in the hardware side, we call it is the thorough hardware functional verification. So once these two are there, we reduce the chances of bugs in the end product. This slide gives the high-level SoC design flow. Just to recap, so things start with customer requirements. So customer gives a requirement of a particular application that I need SoC for this and this application. What the architecture or the architects architecture team does is that they map these customer requirements into a particular architecture that can be implemented that will satisfy all the customer requirements. And this architecture document becomes as a golden reference for the SoC design team to implement the SoC based upon this specification. The next step in the design flow is to put the SoC together, and this is done at the RTL level, which is register transfer level. And this is usually done in hardware description language like Verilog or VHDL. We collect all the IPs together. As we discussed before, it's integration of IPs, digital, analog, mixed signal. And the next step is to convert this into the gate level corresponding, map it into actual logic gates. And this process is called synthesis. And what we get is a gate level netlist. What follows is the physical design. So mapping this netlist into the actual layout, where we can see polys, contacts, active layers, and all that, the actual layout of the chip. And finally, this layout is sent to the fab to fabricate into the IC. Now, through this process, through this design flow, bugs can creep in and at different stages. So at the first stage, the integration stage, it could be the person or the team that is integrating the SoC based upon specification. They could have a wrong interpretation of specifications and they could implement it in unintended way. That would be a bug. Wrong interconnections of IPs. So while hooking up all the IPs in a complex IP, it's more difficult because you have 80, 90, hundreds of IPs you have to integrate. So it becomes, so there could be a problem of interconnection when you are hooking the IPs together. This could be source of problem. Then IPs itself could have, IPs themselves could have logical bugs inside their RTL, inside their own RTL. The next stage is of synthesis. Here, there could be a problem of mapping the RTL to gate level netlist, which is done by synthesis tool. But since it's done again by humans, there could be setup errors in the tools. That could be a source of bugs. And also the way the RTL is coded, and it is not synthesis friendly. So that could lead to some synthesis problems. And the tool itself, sometimes, although rare, but tool themselves could have some bugs. Then at layout stage, now we have the timing also in the picture, and there could be timing problems created because of all the parasitics that we have in the layout stage. The RLC, resistors, inductor, capacitor could cause setup hold violation and timing problems. So these timing problems could manifest themselves as real bugs in the final product. When the silicon is actually manufactured, there could be defects like wires could be shorted, wire could get shorted. In smaller technologies, it's a bigger possibility of this happening. and or they could remain open. So there could be manufacturing defects, which could also be source of malfunction. Okay, so next we see now what is the impact in terms, what is the financial impact in terms of the bugs, not only financial, also on the effort. So cost of, let's call it the cost of bugs. Now, this is the design flow again depicted, and the blue boxes, as long as we are in the blue boxes, we are in the software form of the SoC. That means we are in the form of files on the computer system. And on the right side, we are in the actual hardware form, which is silicon. And then it goes into product, and of course, that is also hardware. So software form and hardware form. Now, if the bugs are found at early stages of design flow, okay, we expect to find some bugs, and they're easily fixable because we are in very initial stages. Now, if we move on to the next stage, the bugs found here need a little bit more effort to fix, as they must also be fixed in the previous RTL source, and synthesis has to be redone. And so it is more effort and time consuming here. So development schedule could be affected, may or may not be affected. Now, when we come to the layout, this is the more advanced stage of development. And here the effort need, if we find a bug around this time, the effort needed is high. And it must be fixed in all the previous stages, right from the source to this stage. And the layout will have to be regenerated also, may have to be regenerated if there is a complex bug. If there is a simple bug, it can be fixed. There are techniques to fix it, but if it's a complex bug, it has to be completely relaid out. Project schedule at this stage most likely will be impacted. Now imagine that if bugs are coming at SoC silicon stage. Firstly, it's very difficult to find the root cause of the bug, because the visibility into hardware is not there directly. We don't have direct signal visibility as we have in the previous stages. We don't have it in hardware, so it's very difficult to debug. So it's very time effort consuming. And bug fixing. So first approach is that, do we have a software workaround? Can we work around this bug through software fixes? If not, if it's a fatal bug, then we have to fix it right from the beginning and going through the entire process again, and then a remanufacture of the SoC. Now, which means that it is very costly in terms of schedule and money at this stage. And then if the bugs actually come into the products which are in the hands of the customer, it costs extremely high, because now company reputation is at stake. Customers' trust for that company or that brand is at stake. There could be legal claims also in certain cases. The company may be sued, and there could be product recall costs. There are some cases where the cars are recalled just to replace a particular IC, a particular module, or get a software fix. So that involves a huge cost. Bug fixing costs, of course, are there, and the product has to be requalified if the bug fixing is done before they get into the final product. They cannot enter the final production stage without a requalification. So it's extremely expensive. So that's how the cost of bugs increases as we go through the development cycle into the end products. Now, just compare this cost with a software bug fix. In case of software bug fix, it would be fixing software and then getting in, making a software update. But it is not the case in hardware. It's extremely, extremely expensive. So by now, we have an idea of why actually we need functional verification. Bugs, we know, are really bad. and they must be prevented from reaching the end product because the end user expectation is that of flawless operation. Bugs are costly and must be discovered as early as possible in the development cycle. We saw this. Bugs can be plain annoying, as in the case of burnt pizza, hanging phone, or it can be dangerous, as in case of a robotic surgery or in case of vehicle developing a problem at high speed. So the sole aim of hardware functional verification is to ensure that no bugs reach silicon. So this covers the first portion, which is the why part. And now we will move on to the what part of SoC verification. What do we actually do? What is involved in SoC verification? We'll try to cover these topics, the functional verification problem, hierarchical verification approach, how verification fits in the overall SoC design flow, verification goals. What are the verification goals at SoC level? What is gate level verification? What is low power verification? How do we handle analog blocks? Okay, so functional verification problem. So as we discussed, everything starts, the design team's job starts from the specification. So assume this is the specification given to the design team. Create a design, the output of which y is the output, gets the value 1 only when A and B differ in their logic value. And the output should get value 0 when A and B have the same logic value. So this is the design specification. The design team implements the design. And verification problem now is to check or verify that the implementation meets the specification in all possible input conditions. So to the verification team, the design is really a black box. The inputs, actually verification is done with respect to the specification, irrespective of how the design has actually been implemented. It could be implemented using XOR gate or AND OR gates or any other implementation. But to verification team, it has to meet the specification. So following a logical approach, we take the design. Okay, verification team would take the design, and from the specification, we'll try to see what the expected output will be or should be corresponding to all the possible design inputs. So in this case, we have 2 inputs, so we have 4 possible input combinations. And for each of these input conditions, we calculate the expected value y based upon the specifications. So if it is different, it is supposed to be 1, and if it is same, it's supposed to be 0. So what next? So next is to actually stimulate the design with the input conditions, and we call this a stimulus. So we stimulate the design with stimulus, and we check for each of the stimulus, the output is corresponding to the expected output. This is plain concept of verification. Very simple. Now, the same thing is if we talk in verification language, so how would we implement this? So we take the design and we call it as a DUT, which is design under test. This is verification nomenclature. And then we create a test bench around it. Okay. And the test bench just implements the concept that we discussed before. So it has a stimulus generator or a stimulus driver, and it will be connected to the design to generate all the possible input stimuli. Then it has monitors placed at input and at output, which will continuously monitor the inputs and outputs. And it has also got expected output generator from the spec. So the verification engineer knows the spec, so they can code in the test bench the expected output. So if we monitor the stimuli and for each stimuli, we now know what is the expected output. We feed it, feed the expected output and the actual output of the design to a comparator. And in verification parlance, it's called a scoreboard. And if the comparison passes, then it's a pass, else it's a fail. This is how simply same concept is implemented in verification. Moving forward, now we saw a very simple example, 2 inputs, 1 output. The real world SoCs have got millions of such components, not just thousands or lakhs, millions of such components. And we start with simple, how we create SoC. We start with simple building blocks like combinational elements, sequential elements, state machines, etc. And then we create IPs out of them, which could be simple or complex IPs, processor cores, very complex IPs, and other IPs like UART, I2C, etc. So these are created from simple blocks, and then IPs are integrated to create SoCs serving a particular purpose, which could be microcontrollers or microprocessors or application-specific ICs. So what is happening here is that we have RTL code. From a few lines of RTL code, now we have hundreds and thousands and lakhs of lines to deal with at SoC. RTL code has increased. Number of inputs and outputs have obviously increased in SoC compared to a simple IP. Conditions to check. This is also increasing as we go to SoC, and states that the design can reach. Now it's a complex combination of complex IPs. So states are also increasing that the design can actually reach. So how this complexity is actually handled at SoC. So what we normally follow for a small IC, it is okay. You can handle it. You can have SoC level test bench and verify it. But for a bigger SoC, which we discussed, which has scores of IPs and processors and complex SoC. So for that, what we take is hierarchical verification approach. What is hierarchical verification approach? So here we start with the IPs. Verify the IPs, and this is done by dedicated IP verification teams. And what is created is IP level test bench around the IP, and IP logic is thoroughly verified. So this brown color logic is thoroughly verified with the IP level test bench. Now subsystem. Sometimes we club together IPs which are related to a particular functionality. Let's say it's a camera and display. So camera interface and display interface and video stream processing IPs, we would club together into subsystem. So this subsystem is now to be verified with a subsystem level test bench. Again, the complexity is not as much as IC, because now we are dealing with a few IPs integrated. And the aim is to verify the logic between the IPs, because IPs are already verified at a lower level of hierarchy. So we don't need to re-verify the logic which is inside the IPs. We need to verify the logic which is between the IPs. And the next step is then integration of subsystems and IPs into SoC. And again, the goal here is to verify the logic which is not yet verified, which is the logic outside of the IPs and subsystems, which includes connectivity, glue logic, whatever logic you have outside with SoC level test bench. So this approach is typically followed to verify a complex IP, complex SoC. If it's a simple SoC with a few IPs, you can directly have only the highest level. You can just have SoC level test bench and verify the entire logic along with IP logic, everything at in one go at SoC test bench. Okay, so what is it that we really check at SoC level? Um, this is a list of some items that are typically, the target of SoC level verification, the goals of SoC level verification, which is correct integration of IPs, the connectivity. It's possible when you are connecting the IP in the SoC level netlist, some of the connections are wrong or not even connected. So that has to be checked. Interaction between the IPs. So IPs and IP level test benches may be working fine. Everything is working fine. But when you try to put two or more IPs together and there is interaction or communication between the IPs, one has to make sure that that also works. Because sometimes, because IPs are developed, if they're developed in isolation, then there could be some assumptions of communication and that have to be verified. So interaction between the IPs have to be verified. Clocks and resets connectivity. So in complex ICs, you can have several clocks, several frequencies, gated clocks, ungated clocks, several types of resets also. So how we make sure that each IP gets its correct clock and correct reset. So this should be verified. Boot up sequence should be verified because when you are booting up, that has to follow a particular sequence. You cannot be booting up the processor core before booting up the rest of the system, before deasserting the reset to rest of the IPs, because processor core will just start to access and it will be accessing IPs which are still in reset. So there has to be a particular boot up sequence that has to be followed in booting the IC, that has to be verified. There is ROM code after booting up, the processor starts to execute the ROM code for initialization, etc. But that ROM code is actually coded in hardware. Okay, so it is not like we can upgrade it later or patch it later. It's actually in hardware. So this ROM image sits in the chip and it is hard coded and it has to be verified as well. In multi-core, multi-processor systems, there is also a big requirement of coherency. If this is a requirement in the chip, that has to be verified. The entire system has to work coherently. So cache coherency has to be verified. Stress scenarios on resource arbitration points. So there can be points like the entire chip can have, let's say in this case, there is one RAM for the entire chip, and all the IPs, including the processor core, will try to access the RAM, which is a shared resource to different IPs. Now that becomes an arbitration point. The RAM becomes a shared resource, and there is some arbitration in case of multiple IPs trying to access it at the same time. So there have to be stress testing there, that if there are multiple IPs accessing, then the system should still work. It should not get hung. Performance checks, if any of the data paths are getting stopped. It's possible that if one IP is the only one accessing the memory, it's working fine, right? But if four other IPs are simultaneously accessing the memory, then this first IP is getting starved of the data. It is not getting the data it needs and has to wait for for all the other IPs to finish. So those kind of problems will create a performance problem for this particular IP. So that has to be verified. Then finally, application use cases, scenarios, and this is the list that comes from customer application. So one has to have understanding of customer application, and then those use cases which actually will be used in a product, say IP will be used in a particular configuration, that has to be also covered in verification at the SoC level. And this is just some examples, but based upon particular chip, there can be, the list can grow or it can also reduce. So how does verification verification fit in the SoC design flow? So previously we saw SoC specification, then it can gets integrated into SoC level RTL, then synthesized into gate level netlist, and finally into physical layout. So the verification has to be done. The SoC verification has to be done for two abstractions of the SoC database. One is at the RTL level, that is before synthesis, and then it is at the gate level netlist, which is actually corresponding to the actual final layout. So these two abstraction levels have to be verified in SoC level verification. So on the right, let's see how it is done. The very first thing is to plan things out, right? So this is a very critical step. So based upon SoC specification, complexity, the verification, detailed verification planning is done. Here, strategy is decided. Which blocks, how much verification for each block is needed, and there are a lot of other aspects also for verification strategy. How many resources would be needed? What are the tasks involved? And most importantly, what is completion criteria? When do we know that you are done and you can sign off on the verification that go ahead and go to the next step? So this planning phase is extremely important to get it right. Once planning is done, the next step is to create the SoC test plan. And this is where you have the detailed test cases listing, what exactly will be done. Basically, it's a listing of the test plan for each IP for SoC level, details of what all tests will be coded. Then there is actual implementation of the test bench and implementation of the test cases, actual verification. And once everything passes well, all criteria as decided here are met, then it is a go ahead for the next step, which is synthesis and layout creation. Next portion is on the gate level. So this, and there is a dedicated slide on gate level. We will discuss what it is. But gate level verification is done at this stage, which has all the timing information and gate level netlist. And when everything passes, you give a go ahead, and it can be fabricated. Gate level verification. So what it is? So if you see on the left side, we have RTL verification, which is RTL level abstraction of the chip, which is purely a functional model, which means that it does not model any timing delays. Or in other words, it does not model things to the level of gates and flip-flops, and that it's a high-level description. And no concept of timing delays. But when this is eventually converted into layout, then there is the abstraction level of the netlist it's actually mapped to gates. So it has sequential elements, combinational elements, and it's also at layout stage, we know that there are resistor, inductor, capacitor, all that results into timing. So timing is modeled at this stage, and that information is there. And as we saw before, that can cause also some problem and must be verified. So so how is timing verified? There is a static timing analysis. It's not part of verification. It's a different team that does static timing analysis, and that is the primary method to check timing correctness. It's a dedicated tool for this. But there are some problems that can still come into the database. And these are some examples. For example, glitch. Glitch is like an unintended narrow pulse on a signal that can cause corruption of its fan-out logic. And this glitch is not modeled in STA. This is not checked in STA. Now, we know that in a multi-clock domain chip, we can have clock domain crossing. Okay, so there could be a synchronizer missing on a clock domain crossing. We know that when signal crosses the clock domain, there should be a synchronizer. And if that is missing, so these paths are not checked in STA timing, because those paths are anyway clock domain crossing paths. So those are ignored in STA. Then there are incorrectly defined false paths. Again, STA is again done by humans, so there could be a there could be tool setup issues, and that can cause some of the timing paths to not be checked. And from our electronics knowledge, we know that if there is a setup problem, then we can reduce frequency and somehow work the chip. But if there is a hold problem, then the chip is pretty much dead. It has to be remanufactured. So it can be these kind of problems. So what is the flow? For gate level, we take the same test bench as RTL. We take a subset of the tests. We don't run all the tests on gate level, just a subset to get enough confidence. Gate level netlist is coming from the backend, the layout database, and the timing information is also coming from the layout database, and that is then simulated and checked with those tests. And this is we refer to as timing simulation, timing simulation of the gate level netlist, and some of the issues can be caught here. Okay, low power verification. So what is low power design, and why do we do it? So it's uh, let's say a particular chip, right? It has got two processors, and for a particular application, we need only one processor, right? So why not just switch off? And what is the reason to switch off? Because we know that uh, it consumes power, because any logic that has got power will consume power. If it is actively working, actively nodes are toggling, it will have dynamic power consumption. And if the clock is even switched off, still it will have static power. So as a power saving techniques, the unneeded IPs or unneeded features, the power is just gated off to that, and gating off is done using a PMOS switch. So once power is gated off completely, so we eliminate both the dynamic as well as static power. So this is the motivation for doing power gating of some of the blocks. And this is in the low power architecture of the design. Now, what problems it can cause? It has to be done. This low power designing has to be done very carefully, because it can lead to some problems. Example is that if you switch off the power to one of the IPs and the outputs are going to another IP which has got its power on, then this node is actually floating, because there's no driver of this node. There's no power in this node. And this, we know that floating nodes are bad. Floating inputs are bad for IPs, because they can be anything from VDD to even zero or anything in between. They can cause functional problems. They can cause power problems. So we don't want to give floating inputs to any of the IPs. The way to take care in design for this is that isolation cells are placed on all the outputs of the IPs which are power gated. And before switching off the power, you have to switch on the isolation cells. So there is a particular sequence. You switch on the isolation cells, and then you switch off the power to the IP. And when you're switching on, it's the reverse. You turn on the power, then you remove the isolation. So a particular sequence has to be followed. And if that sequence is not followed, then there is a problem. And this has to be verified. So some of the bugs that can be found in low power verification is isolation cells at the outputs of power gating are missing. So some of these cells may be missing, or there is also, it's possible that incorrect power up, power down sequence could be there. And for example, the processor, if it's accessing some IP, and the processor core powers up before the IP, then it would be basically accessing a power gated IP, right? So there is a particular sequence to be followed, and that has to be verified correctly. So this is why we do low power verification. And then purely digital simulation. So this is how we handle the analog blocks in this. So analog blocks, we know that it can have values other than zeros and ones. So there are two ways to handle analog blocks. One is using purely digital models of analog blocks. So a PLL, it can be a complex analog block, but it can be modeled simply as clock generator, simply this statement, and it can be verified. So this approach is used when we don't really care too much about analog blocks. That is not the target of verification. We can use this technique. But in other cases where we actually need to verify the analog behavior of the analog blocks in chip level simulations, so here we use digital mixed signal simulation. This is the latest technique that is currently being used. And here we use the real number modeling feature of system Verilog. So here what it allows is it allows to model analog values on the ports of the blocks. So thus enabling creation of a real number model of analog blocks, and it can be simulated in the digital simulation itself. But analog behavior can be modeled and simulated and checked at SoC level using real number models. Okay, so this brings to just a thought slide on, and this, by the way, the last slide. Desirable qualities, in a verification engineer. It's sorry about this spelling mistake. So one is appreciation of the end use of the IC. So while verifying the SoC, one should always know and understand what is the end application, and from there try to bring that application use cases into the verification test cases and try to prove those applications. So this is important to understand where it's going to be applied. Imagination. So this is a very important quality, because here we need to be very imaginative about the scenarios that can happen, how different IPs can operate together, in what conditions. So all this depends upon how good we can imagine the scenarios. Creativity is, of course, very important, because eventually we are creating test cases for this. We are creating test benches for this, and as you know, the code can be created also very efficiently or inefficiently, and depending upon the creativity of the person creating. Hacker mentality, so in a good way. So this is the quality is very important to actually have a mindset that no matter how good your RTL is, I can find a way to break it. I can do a test that will expose a bug in your RTL. So this is the mentality that is needed to have a good test plan, to have good verification done, and then healthy paranoia, in the sense that you should always be feeling that there is bug present. No matter how much verification you have done, there is still a bug there waiting to be found. So that you never rest. You always continue to think about scenarios, in your dreams, in your daytime, that how you can find that bug which is lurking somewhere in the design. So this is what I mean by healthy paranoia, and eventually that leads to discovery of very, very corner case scenarios and good quality verification in the end. So with that, we have covered the what portion also, and that brings me to the end of this first part. of SoC Verification Overview. We can open for any questions, comments.
Thank you, Swinder, for giving us such a enlightening, I'll say, enlightening session to us and to our viewers on what and why part of SoC design verification. So maybe we'll start with few questions,
Yeah,
and yeah, so we'll seek your like towards like at the end of such session few highlights or few things which could be transferred like which could be shared to our viewers, so we'll go ahead with that. So
sure.
maybe like we can start with the in the current era there is advancement in each and every technology that we are seeing into. Things are moving in a very fast way, in a flash manner kind of thing. So
Right.
like how does verification landscape is evolving, and what are the new trends or tools that you foresee which will become integral part in the near future? So that will something which will be good for the students who are watching us or who will be watching us in future, that will give them uh, some insight to be prepared for this domain, or to expect few things that would come in future. So if you
Okay.
could
Perfect.
share
Perfect.
something.
Perfect. So this is actually the topic that we will cover in detail in the how aspect, where we will cover the tools that are currently used, that were used previously, how they have evolved, and how they are currently used, and also on future outlook. But definitely, things are also changing very fast on the verification front. And now we are also seeing, things like formal verification, which are getting more widespreadly used, and also AI and ML. So that is finding its way in verification as well. So we will talk about this in details in the next part.
Thank you, Ravinder. So maybe like if we go from students' point of view, so if there are few like if some of the students or if some of our viewers are interested to pursue their career as a associate design verification engineer, so what knowledge, like when they are in say in their second year or third year, what sort of knowledge should they start acquiring so that they are ready to come into this industry? Or what should they
Okay.
focus for?
Okay. So I would not say just for verification, but I would answer it in a general term that we tend to ignore certain areas which we feel are more involved, more difficult. I've seen this, right? So my recommendation would be that basic electronics, you should have very good knowledge of that. Digital electronics, um, you should master that. And about the processors, because I don't know, nowadays it's 8085 or 8086. We studied on 8085. So how that processor works, the assembly language, how the interrupts are working, very good, how the data is getting transferred. So this is something that part of the curriculum, that already part of the curriculum, and people should do it very nicely. And also to take things to the next level, also search the web for different articles on SoC, where things are going, where things are going on the memory front, on SoC front, which are the tools coming up, which are the languages. So combination of all this, I think people should do. So by the time they graduate or they're ready to leave their college, they are well equipped with the basic knowledge.
Thank you, Ravinder. So it's really, so it's like foundation should be strong. So then,
Yes,
like all of
absolutely.
us need to work on our basics. So there's a
Yes.
question from Mr. Prashad CVS. So he has a question that what are the entrepreneurial opportunities in verification? So
Okay. So today what we are seeing in the industry is that a lot of service companies are coming up, and they almost all of them start with verification as a service first, and then go on to other areas. So many entrepreneurs they offer to verify as a service. This is one opportunity. Another is that what we use like IPs, right? Common protocol IPs like UART. So many companies really don't want to invest in creating a verification IP for UART. Let's say a driver or UVM test bench infrastructure for UART. But one opportunity could be to create such VIPs, and then offer it to the companies, because companies themselves they are looking for vendors who can help them handle these common IPs. So that is another area uh, that is there
Thank you.
that people are doing.
Thank you, Ravinder. So we have one question on how on STA. So how static timing analysis can be done on Vivado software and Cadence. So it is asked by Mr. Balas Sinduri Kandula. Pardon.
Okay. So actually, I am not expert on the STA domain, so I cannot answer that specifically on the tool. But I do know that tool called Prime Time was used in STA, which I worked with for some time. So I don't know about Vivaldo tool, is it, or uh, yeah, I don't know about this because I'm not expert in STA domain.
Thank you, Ravinder. So we have a general query from Mr. Mir Shawaz Ali. So his question is why semiconductor industry is not hiring freshers? So I
Why
don't know, like,
semiconductor?
yeah, is not hiring freshers.
No. So, Mr. Ali, so that maybe see. What I observed from my time in semiconductor is that it's cyclical in nature, right? So we have phases where we have lot of people looking for opportunities, including freshers, and we don't have any opportunity, right? Any opening, but we also have phases where we have a lot of opportunities open, and we don't have people, right? So when we are in, unfortunately, we are in a phase where we have a little bit slowness of hiring, but this phase will not last forever, right? So, but semiconductor industry doesn't hire freshers. That is not right. Uh, we have hired, in my career, we have hired freshers and also interns. We have also given internships and also internships plus placement offers. So it's not true that semiconductor industry does not hire freshers.
Uh, thank you, Ravinder. Maybe like so regarding this STA question, we have Dr. Pradeep Thakur volunteering that he
Okay,
could throw some highlight on that. So I request Dr.
sure,
Pradeep Thakur to please, if he
sure.
can share something.
Sure. Thank you, Sushma. So within Vivado, so there are two kinds of timing closure. There is one that is silicon specific timing closure. Other one is FPGA specific. So when you are doing SoC or when you are doing ASIC, then you have the tools from Cadence, Siemens, and Synopsys that are used as golden sign-off tools for STA. When you're doing FPGA with Vivado, Vivado has its own inbuilt timing checks, and if you sign off on the Vivado timing checks, then they guarantee that when you map it to the FPGA, the design is going to meet the timing it's reported. It is also common practice if you are in case if you're seeing timing problems. It is also common practice to use gate level simulation to debug the FPGA timing issues. So the FPGA tools, whichever you take, whether it is Xilinx or others, they provide integrated solution starting from RTL synthesis to the timing sign-off. And if the timing is a problem, then you use gate-level simulations with timing files to debug whether there is some constraint being missed, or tool is not able to close the timing, etc. Right? So that's the context. Thank you.
Thank you, Dr. Pradeep Thakur. So maybe like since now we have no more questions, we'll call this session off. So on behalf of everyone, like on behalf of all our viewers who are watching, who will be watching, and on behalf of ISA community, I thank I thank Mr. Ravinda, and also like for sharing this the knowledge he has in this session, and that will definitely benefit our viewers in their academic pursuit, and also in the future endeavors that they'll be doing in this field. So thank you once again for your time, for sharing this expertise with us, and we would definitely look forward to the next session when we'll hear from you about the how part of this SoC design verification. So I request everyone to please stay tuned for our next session where we'll complete this cycle on SoC design verification. So thank you so much, Ravinder, once again.
Thank you, Sushma, and thank you, ISA, and looking forward for the next session.